Up next, we have the first team from the University of Florida, Rayo Veloz. They will be presenting on bus rapid transportation system. Please welcome Daniel Ruiz, Judith Labrada, and David Lebron.
Good morning, everybody. Thank you for your time. My name is Daniel Ruiz. I'm a third-year civil engineer at the University of Florida.
My name is David Laram. I'm a fourth-year civil engineer at the University of Florida.
And my name is Judith Labrada, and I'm a fifth-year environmental engineering student at the University of Florida.
So today, our team, Rayo Veloz, will be presenting our system of bus rapid transportation. Next slide. So our agenda for the day is first we'll be talking about the current situation in Havana. Then we'll present the BRT as a solution. And then third, we'll talk about some of our objectives and our methodology.
Thank you, Daniel. So when we first started with this project, we first analyzed the current transportation options available to the citizens in Havana. And what we found that is there is actually only a small amount of privately owned vehicles in Havana, only around 37 for every 1,000 residents. Mostly, everyone relies on public transportation, biking, or walking. Slide. And what we found when we dug a little deeper is that this has caused a lot of stress on the public transportation system, which means that it has been disorganized and has led to a lot of delays and has led to just general unsafety and unreliability. People can't rely on it. And so, thank you, slide. And so our solution to this is developing a bus rapid transit system that can effectively carry people from one end of the city to the other. And what a bus rapid transportation system is a way to combine the speed and reliability of a rail system with the flexibility and low cost of a bus system. And what that's going to look like is a bus system that has its own right-of-way and stationing, has off-board fare collection system, and implements traffic signal priority technology in order to get across the city as quickly and effectively as possible. And so what we looked at when we looked at it is, does this work? And so what we looked at here, you can see the general trend in time as opposed to the number of cities that are currently implementing BRT systems in the world. You can see that over time, more and more cities are turning to BRT as a solution to their transportation problems. And now Daniel's going to talk to you a little bit about our objectives.
All right, thank you, Dave. So some of our objectives with the BRT system is that we wanted to make sure that we determine all of the time-saving possibilities, because that's what's going to make our system attractive to the people. And then once we've done that, we need to make sure that we're designing the right infrastructure that is going to maximize this time savings. Next slide. So what did we do to analyze time savings? So first, we had to look at the different type of running ways, because BRT system has different type of lanes. And then second, which I think is one of the most important to determine the success of a BRT system in a city, it's estimating the ridership. Next slide. So the way that we came up to decide what type of lane we will use, we came up with our engineering judgment, and we did a decision matrix comparing 5 different factors: capacity, cost, least space required, identity, and the time savings. So we compared the 4 different class of lanes that we have, which we talked about in our paper, and we decided to go with class 3, which is median arterial. And the reason for that is because that's the one that goes like in the middle with all of these factors when it comes to time savings and cost and identity. Next slide. So literally on this type of system that we're trying to implement in Havana, time does translate into money. So we're looking to maximize every possibility of time saving. Next slide. So as I mentioned before, our ultimate goal is to design the right infrastructure that is going to maximize those time savings. So as I talked about the lanes, why did we choose median arterial? Because those type of lanes is going to increase the time savings of 1.5 to 2 minutes per mile for each lane. And not just that, but it has the capacity to carry 200 buses per hour. So as you can see, that's definitely going to maximize time savings for people to get from one area of the city to another area. So next part. So now I'm going to focus on the stations. So as you can see on this slide, we decided to implement center stations. And the reason for that is because that's going to give access to the passengers to both directions of the buses, rather than having two different stations for each corridor, for each lane. So not only that, but that's going to minimize the construction cost. And then it's also going to minimize the right-of-way, which is definitely a huge factor when designing these lanes. And not just that, but we took into consideration two very important factors when it comes to parameters. And the first one is the length between each station, because that's very important. So the length between each station depends on the type of routes that we have, either if it's a limited stop or all-stop route. And then we also took into consideration the distance from each intersection to the station, the setback length. And the reason for that, as you can see in here, which is 85 to 130 feet, is because we don't want the intersections to start to delay the buses from the buses that are coming behind them. So that's the reason for that minimum length between each intersection and each station. Go to the next slide.
So for ridership estimates, we actually had a very difficult time assessing ridership estimates because we didn't have access to things like surveys and average times and distances people needed to travel. So what we had to do is we had to look at another median arterial bus system that is currently operating in another city successfully. And that led us to choose Bogota, Colombia, because they have their bus rapid transportation system has a similar dependence and mode of transportation for this city as we do. Slide. And as you can see here, ever since its inception, the BRT, also known as the Transmilenio, in Bogota has increased in ridership. And so what we were able to do was take those growth rates and scale them to the population of Havana just to get a rough estimate of what we can expect. And what we can expect is at the end of the first year, around 269,000 riders per day. And that growth rate will grow to around 400,000 by the end of our period that we scaled to. Slide.
So now go back to the video. Should pop up. Oh God. Let me see, because it popped out last time when we tried it. All right, we'll go back into it if it works. We tried it at the beginning, but.
Okay. So something that we wanted to make sure we considered when designing our BRT system is sustainability. And what that means for us is it sustainable? Can Cuba sustain this infrastructure, as well as how can we lower or mitigate environmental impact? And one of the main issues, or I guess environmental stressors you can find resulting from transportation is air emissions. And with the BRT system, because we provide an alternative mass transportation system or mode to transportation, we're able to lower those environmental stressors, as well as the specific technology that we'll implement. It emits fewer air pollutants than traditional cars or other modes of transportation. So the vehicle or the brand that we decided to go with is the New Flyer. The New Flyer is a trusted American brand. They do have manufacturing here in the United States. So it would be easy for Cuba to utilize those resources when necessary. They provide better diagnostics and customer support that overall contribute to approximately an average 26% cost savings, as well as the better distribution of the tires. They provide longer wear, so that results in cost savings as well, and reduction in waste generated. And this is the specific model that we decided to go with, the 60-foot stylized articulated New Flyer. We're going to partner that with a clean diesel hybrid engine, and because we chose to do that, we get all these environmental benefits, like a 5.1 miles per gallon fuel economy, as well as, I think the most important one that we thought was very significant is the 90% reduction in PM particulate matter, carbon monoxide, and hydrocarbons, which they do impact environmental health as well as public health. And lastly, or another big contributor to the BRT is branding and integration. These buses, they're able to be customized to the area that they're servicing, so we can decorate them to reflect the Cuban culture and people. They're comfortable, they're efficient, and the people will be able to relate to them. They'll be the best way and the fastest way to get around in the city, resulting in just overall representation of the Cuban pride and ambition.
So in order to maximize our time and cost savings, we also implemented a few intelligent transportation system technologies. And what that's going to look like is we are going to have a main control center that can track all of our buses using GPS and then adjust lights at certain intersections to allow the buses to stay on their designated schedules. And so right here, you can see a flow chart from the city of Portland just as an example of what this decision process might look like. To where if a bus is behind schedule, it can either extend a green if the light is green when the bus asks for a request, or reduce a red in order to get the bus through as quickly and efficiently as possible. And we have a simulation of what this will look like. Hopefully it works.
We tried the videos before starting the presentation, and I don't know why. We'll try them at the end again, just for the sake of time. So right now, I'm gonna talk about a little bit about the cost analysis that we had to do. I gotta say that it was really hard, since a lot of the cost analysis for a BRT system, you need side data, you gotta do studies to analyze the ridership estimates. So we didn't feel comfortable with giving a set price for the entire project. However, we decided to break it down more into a phase cost, which is also very common for transportation projects. So we broke it down into the cost per lane, per mile. So for example, as you can see in here, the biggest cost will obviously to construct in each lane, since we're taking a lane from the traffic and building its own right-of-way for the bus. So we got an average of about 6 million per lane per mile, and then there's also cost for acquisition of land, even though that cost might be reduced due to the fact that we don't have to build new lanes or new spaces. Since there's already lanes in there, it will be more like maintenance and making sure that they're up to the standard of the BRT. And then we also took into considerations operations and maintenance cost.
For our intelligent transportation system costs, we also had trouble giving a set price. So what we did is we took the ranges from the TCRP report 90, which is cited in the paper, and we were able to find a minimum value needed for a control center of just over $1 million. And then also we broke it down into cost per bus and also cost per intersection that you implement a traffic signal priority. Excuse me.
All right, so let's see. We're going to try again if the videos can work.